We want to learn what happens at reverse bias. Okay, we want to look at the reverse bias. As we know, the reverse bias, you have less current. So what happens is, when you apply a voltage, this is the voltage across to the PN junction. If you apply a negative voltage to the P, positive voltage to the N, it means that we are reverse biasing the diode. Reverse biasing the diode means it's more difficult for the depletion region will increase, right? That's what we learned just now, previously. But in terms of energy diagram, how does that look like? For reverse bias, what happens is this potential difference increases. So what happens is you get stuff like that. The Fermi level is no longer continuous. So you have your conduction band. So the gap Eg is still the same. Okay, whether it's forward, reverse is a parameter due to the material. So the material doesn't change, the Eg doesn't change. So since it's still N, I'm drawing the P. We make the P as a reference. So now the P is like still the same. Now I'm drawing the N. So the N is like that, and the Fermi level is no longer continuous, and still N, the Fermi level should be close to the conduction band, so it's there. Okay, so what happens in the middle, you just need to just connect the two energy band diagram. So the purple line here is the energy band diagram for reverse bias. I purposely draw on top of the zero bias so that you can see the difference. So the difference in the potential here, so if I draw here the difference here, you can see that it's become greater. So this difference here is actually the EVBI plus the V reverse. Okay, so as EVBI plus reverse, because the reverse voltage or field is in the same direction of the field of the built-in field, so it's actually increasing the barrier. So electrons are like balls, and holes are like balloons. So if I were to draw this, so electrons, if majority of electrons are here, you can imagine it's very difficult for the electron to climb the hills to go there. So it means there will be very little diffusion current. So because it's difficult for the majority electron to diffuse for N to P, and vice versa. The holes here is like a balloon or like a bubble. Then bubble would like to go to the top, right? It can overcome barrier. So it's difficult to overcome this barrier here. However, there is some diffusion is very little in reverse bias. However, there will be some drift current. Remember, in reverse bias you have IS in the diode equation. IS is the saturation current. So this saturation current is actually due to the drift current inside the PN junction. So how does this works? Let's see. So the drift current is actually, if you look here at the P, there are minority electrons, right? Electron like balls. If the electrons are at the hill here, and at top of the hill, you can see at the bottom, the electron will drift down. The same goes here. You have minority holes here, so only a very small. When you say minority, you know the numbers from before is very, very small compared to the majority carriers. So you have, statistically, you have some very small numbers of hole will go up there. So this process is called drift. Drift is due to electric field. So the difference, the potential difference, the distance here is due to the drift. So you have some very small drift current, and hence this drift current gives rise to the saturation current. Okay.